Dear friends, today I will discuss some questions from the subject Electronic Science from the exam of December 2019 NTA UGC NET. Fine. So I have taken some questions and these are basically from Unit 1 and Unit 2 of the syllabus. Fine. And I will proceed now one by one. Question number 1. The equation for Fe is the Fermi-Dirac probability function and is 4 options are given. Number 1 is 1 divided by 1 plus exponential e minus ef divided by kt. Option 2, 1 divided by 1 minus exponential e minus ef within brackets divided by kt, and so on. All these options are given. You can read it properly. Fine. So the answer is option number 1, that is 1 divided by 1 plus exponential e minus ef within brackets divided by kt. And now I will discuss some hereabouts of this question. Okay, so f of e is Fermi-Dirac probability function or Fermi-Dirac distribution function. It gives the probability to find the electrons in a given energy level, but it does not give an idea of how many such levels are present. We can say this is a disadvantage, that it does not give an idea of how many such levels are there. Okay, but the advantage is that it gives us the probability to find the electron or electrons in a given energy level. Okay, according to quantum mechanics, f of e equal to 1 divided by 1 plus exponential e minus ef within brackets divided by kt, where e is given energy level, ef is Fermi energy level, k is Boltzmann's constant, and T is absolute temperature and its unit is in Kelvin. Fine. Now I will proceed to question number 2. Question number 2 says, in a PN junction solar cell under low injection condition, the one-dimensional continuity equation or 1D continuity equations are. So the options are option A, Gn minus Np0 divided by tau n plus 1 by q d Jn divided by dn equal to 0, and the options are shown. You can read it properly. Fine. Actually the choices are given in a combination, so choose the correct option, and the correct option is A and C are correct. Option number 3. So we will analyze about the answer. Okay, we know the 1D continuity equation for a PN junction is, or we can say the continuity equations are Gn minus Np minus Np0 whole divided by tau n plus 1 by q into d Jn divided by divided by dn equal to 0, and similarly Gp minus Pn0 divided by tau p minus 1 by q into d Jp by dn equal to 0. These are the continuity equations for the n-type and p-type materials. Fine. And where tau n and tau p are the minority carrier lifetime or lifetimes, Np minus Np0 and Pn minus Pn0 are the excess concentration, and this will be highest near the edge of the depletion layer and will exponentially decrease as we move away from the junction, eventually reaching to 0. Fine. Here Jp and Jn are the current densities, and Q is the magnitude of electronic charge, that is 1.6 into 10 to the power minus 19 coulombs. Fine. Now I will proceed to question number 3. Question number 3 says, thermal runaway in a transistor biased in the active region is primarily due to, and the options are A, heating the transistor, B, changes in beta which increases with temperature, C, base emitter voltage VBE which decreases with rise in temperature, and option D is change in reverse saturation current due to rise in temperature. But these are not the exact options. The options are given in some combinations, and when we analyze the answers, the correct answer will be option number 4, that is C is wrong and D is correct. Okay, and other combinations are not right. So the combination which is given in option 4 is correct, and I will analyze this. So what is thermal runaway? Thermal runaway occurs in situations where an increase in temperature in a transistor changes the conditions in a way to cause further increase in temperature, leading to a destructive effect. We can say that thermal runaway is a destructive effect. Fine. In an unstabilized transistor it occurs and it is a destructive effect. Okay. It is a kind of positive feedback, we can say, and it can be avoided by the negative feedback provided by the emitter resistor in a self bias. Okay, and now I will discuss some more analysis that how with the change in reverse saturation current and due to rise in temperature, what happens. That means I will analyze option number, or I will analyze the option D here. So we generally use a collector emitter configuration in a transistor, and here we know that IC or collector current equal to beta IB plus beta plus 1 within brackets ICBO. What is ICBO? ICBO is reverse saturation current and it depends only on the flow of minority charge carriers. And we know that for p-type material, electrons are the minority charge carriers, and for n-type material, holes are the minority charge carriers. And this minority charge carriers depends on temperature only. Fine. Okay. So when temperature is increased, concentration of minority charge carriers also increases. This sign, that means this is the upward arrow sign, is for increase. Fine. So when temperature increases, concentration of minority charge carrier increases. Then this increases the ICBO or the reverse saturation current. Okay. And when reverse saturation current increases, also beta plus 1 into ICBO will also increase, and so IC will increase because the equation is like this. Fine. If this one increase, this will increase. If this one will increase, the total IC will increase. That is, collector current will decrease. The collector current will increase. That means we can say that IC is proportional to temperature. IC is, or collector current is directly proportional to temperature. Okay. Also, one thing to remember here is that with every 10 degree increase of temperature, ICBO is doubled. It doubles the ICBO, and so IC also changes. Fine. Also, we can explain this in a cyclic manner. When we can say, when T increases or temperature increases, ICBO increases. When ICBO increases, IC increases. When IC increases, increase in heat occurs, and this again raises the temperature. So in a cyclic manner this happens, this occurs. So with this cumulative cyclic process, IC increases and the value of this IC or the collector current reaches to such a large we can say quantity that it burns the transistor. Fine. So for these reasons our option number 4 will be the answer. Fine. Okay. Now I will go to question number 4. If the forward bias is applied to the diode, holes are injected from P side to N side. The concentration Pn of holes in the N side above its thermal equilibrium value Pn of 0 is given by. Again, so many options are given, and out of this, option number 3, that is Pn0 plus Pn of 0 exponential minus x divided by Lp within brackets will be the answer. Okay, and I will explain this through my analysis. So here in the diagram you can see that we have a PN junction and it is in the forward biased mode because P material is connected with the positive voltage and N material is connected with the negative voltage, and this is the depletion layer and other things you know it very well. Fine. In forward bias, the negative terminal is connected to the N type and the positive terminal is connected to the p-type. Hence the externally created electric field will be in the opposite direction of the built-in electric field, right? So built-in electric field occurs within this, and external electric field will be this, and this will be this will be opposite in direction to the built-in electric field. Fine. Next, this external electric field causes the electron to diffuse from n side to p side, which increases the diffusion current by the applied voltage. Fine. We know the distribution of excess hole concentration in the n region is an exponentially decaying function of distance. Function of distance. Okay, so we can say Pn of x equal to Pn0 plus Pn of xn minus Pn0 e to the power minus x minus xn divided by Lp, and these are the n. By deriving this equation we will get Pn0 plus Pn of 0 exponential to the power minus x by Lp within brackets, where Lp is a constant which determines the steepness of the exponential decay or the diffusion length of holes in the n-type silicon. Fine. Xn is the width of the depletion layer in the n side. Fine. So this way option number 3 will be the answer. Fine. Next I will go to question number 5. Question number 5 says, in a Diode shunt voltage regulator, the diode regulates as long as it is kept in what? Okay, the options are forward condition, loaded condition, reverse condition, and unloaded condition. And the correct options are the options are given in the combination form. So among this, the answer will be bit number 2, that is B is correct but D is wrong. B is correct means it must be in the reverse condition, and D is wrong means unloaded condition is wrong. That means condition should be loaded. Okay, here this is the symbol for the Zener diode. Okay, we can say RS must be chosen. RS, this one must be chosen such that IZ, this is the current, should be between INE or Imin and Imax. That means minimum current and maximum current. Here the Zener diode acts as a voltage regulator. Why it is known as shunt volt regulator? It is known as shunt voltage regulator actually because the regulator circuit appears parallel to the load. This is the load. Fine. And that's why our option number 2 is correct option. Fine. Next, the question is, the field effect transistor or FET has option A, very high input resistance. Answer will be chosen from some combinations, and the correct answer will be bit A, that is A and D both are correct. A and D both are correct. That is very high input resistance and low electrical noise. And this is a very normal thing that as the devices are advanced, they should have high input resistance and low electrical noise. So we can also say a FET or field effect transistor is a 3-terminal device having high input resistance or high input impedance, same thing, and less noise. The gate to source junction of a FET is always reverse biased. In amplifier application, the FET is always used in the region beyond pinch off. Fine. Next I will go to question number 7. Question number 7 is, D-lane grove model is applicable in bit A is diffusion, bit B is implantation, bit 1 is diffusion, 2 is implantation, 3 is oxidation, and 4 is epitaxy. So the answer is oxidation or bit number 3. D-lane grove model mathematically describes the growth of an oxide layer on the surface of a material. It is used to predict and interpret thermal oxidation of silicon in semiconductor device fabrication. Fine. And also I